So today we're very happy to have Professor Feng-Li Lin, Feng-Li, from NTNU, from Shidang, to give us today's actually a second installment of Entanglement. So that's pretty nice in that sense. I introduce a little bit more than I normally do for Feng-Li because I find his trajectory very remarkable. He started out as an engineering, double E major at National Sun-Yat-sen University, graduating in 1988. Then he went to Tsinghua, NTHU, and received a master in physics, and spent 3 years somewhat floating around at not just Institute of Physics, but also Institute of Mathematics at Academia Sinica, doing unusual things. Then he went to, in 93, he went to VPI, the Virginia Polytech, and spent 5 years there, almost finishing a PhD. Then courageously, he moved to Utah to become a student of Yong-Shu. I will not give you the full details, you can check with him. So, I felt that's why I spent more time introducing him. So in 2000, he went to Seoul National University as a postdoc, and furthermore at Tamkang University in Taipei, and then also 2 years at NCTS in Hsinchu, and became an assistant professor in 2004 at NTNU, and went through the ranks, and became full professor in 2010. In 2011, he went to MIT for a year's sabbatical leave of some sorts, and he has also been involved in administration support at university side, R&D, and also international divisions at NTNU. So he has done a lot of service work. As far as I can tell, he works very hard, stays active, moved towards string and now then towards entanglement. So I told you his entangled life, and he also writes book reports on China Times. So if you have a book, notify him. Okay, long introduction, many faces of entanglement, and I show you the person here. Okay, floor is yours.
So do I need to use microphone?
Yes, preferred, but it's usually hard to handle.
Thanks, George.
It's great.
It's a problem. So how can I wake up this guy?
你会处理吗？ 长得够高，要不要 push 他一下？
是我这边不行吗？
别 push 太久，它好像是亮着的。它是亮的。可是不知道为什么这个。
它是亮的。
需要？应该不需要，应该变色的。刚才好好的。
对。Thanks for Joe's invitation and long and nice introduction. Yeah, so I have Entanglement Lab, so I now introduce the entanglement to you. Yeah. So the title is Many Phases of Entanglement. This title because in the past few years, I working in various topics which are all related to entanglement. And so in this talk, I will not give you a very specific detail about any topics. My intention is try to do some service to introduce the basic of entanglement, especially on its origin and its implication. And then I go through the trajectory I have been through and talk about something interesting what I think is interesting, okay, about quantum entanglement. And this field is still alive, so you probably will get some inspired and try to look at the literature later on. Yeah. So today I will focus on these 4 basic topics. So the first is about the entanglement non-locality. Actually, this was the original purpose to study entanglement. Start from Einstein and then come to Schrödinger and then go to Bayes inequality. And later on turn into a whole industry for quantum information science. So actually there are lots of infinite number of literature about this issue, and there are still many things we don't understand. And then we try to understand how we can characterize the quantum entanglement, because in some sense it's not the most tricky stuff about entanglement is it's not a physical observable. So we don't have the usual way to understand it by experiment. So basically many studies are on the theoretical side. So we need to, even in this we find it's still very difficult to fully characterize the quantum entanglement. Okay. And then I will go to some other issue which start from 2006, there are a proposal to understand entanglement from the holographic point of view. Means that by using ADS-CFT correspondence, we have a more geometric way to understand entanglement. And also from there, I think many people find that entanglement would be, in some sense, a universal concept to all the field people are studying these days. And so it's quite inspiring to know what this picture means and how it's implied in the later or in the future research. And also I will talk about something about quantum decoherence, which I was recently involved in the studies, some special case. And I will talk about this from the entanglement point of view. Actually, in some sense, quantum decoherence is the entanglement process. So I will just tell you this point of view and see what we can see from this kind of understanding. Yeah. So if you have any questions, just stop me anytime. Okay, and these are the work related to this talk in the past few years. And all the Ray staff are my collaborators. I thank all of them. And some of them are sitting there. So, yeah, so I learned this from many people. Yeah, especially through working on the special topics. Without them, I cannot achieve what I have done today. Yeah. So everything just starts from this paper by Einstein and Lawson, also EPR, right? Then Podolsky, yeah. So this EPR paper, that's famous paper. So it's good if we can just read a paper face to face to understand what's going on in this paper. Actually, this paper is very short, only 3 or 4 pages. So we can, this day it's very easy to access figure review, so we can just download it. And this paper was published on the 1935. Okay, almost how many years ago? Yeah, yeah. And so in this paper, Einstein tried to argue that these two statements cannot be true at the same time. That either the description of reality given by the wave function in quantum mechanics is not complete. Means quantum mechanics is not a complete theory. Or second, the two quantities cannot have the simultaneous reality. So he tried to argue that either one would be wrong. Yeah. Yeah. So if that's true, that means if the two quantities can have simultaneous reality, then probably quantum mechanics is not complete. Yeah. So and it turns out, so this is abstract. So it turns out he finds that the one is not right. Second is also not right. So then he lead to a conclusion that quantum mechanics is not a complete theory. Okay. So here he defines what the reality. Okay. So every element of the physical reality must have a counterpart in the physical theory. Okay. So what does it mean? It means that, for example, we know that if we have we have spin up in the x direction and we have spin down in the y direction. For example, these two spin directions cannot be simultaneous, be physical observable. Okay. So maybe one of them cannot have the physical reality. Okay. So this is why he said that if two quantities which cannot commute to each other have simultaneous reality, then something must be wrong. Okay. And then he must find an example to demonstrate this is the case. So the example to demonstrate is nowadays we understand that it demonstrates that this kind of wave function. Suppose it prepare this setup, okay. It prepare the setup by start a system 1 and 2, and then let them interact for some time. After that, the interaction will turn off, and then send these two systems to each very far away distance, separated by a very far away distance. Then he write down a wave function for this case. Okay, at that time he didn't know this later entanglement inside this wave function. Okay, and then I don't want to go through the detail, but basically he said that we can have wave function in this way. It means that we choose a basis for system 2 or system 1, and then we do the measurement. The measurement is done in the local sense because these two guys are separated in the far distance. So I've done a local measurement at the system 1. Then immediately when I do this measurement, I will collapse this wave function to one of the state. Okay, so it means that the entangled state will become a product state in this sense. After that, you will know this. And then, by some way, he also argued that we can then choose to, for example, here I try to measure the momentum of the particle in the system 1. And then I change my mind. I say I want to measure the position of the particle in the system 1. Then the wave function will collapse in the two different ways. But because no matter how I do this, these two systems are separated far away from. So you assume that if there is no non-locality, you assume that the system 2 will not be affected by what kind of measurement you choose to measure in the system 1. So he then argued that then the system 2 will not be affected by the result. Then simultaneously, then he lead to a conclusion that because there is no change in the second system, no matter what you measure in the system 1, then it's possible to assign two different wave function for system 2, but correspond to the same reality. Because the wave function in the system 2 didn't change, but because I measure the system 1 in different way, I get two different reality, in some way, two different representation. And these two different representations all correspond to the same so-called reality, so the same wave function. And in this sense, they're the contradiction. So he then need to, from this statement, he then say that, okay, then we conclude that the quantum mechanics cannot be complete. Okay. Okay, so I have said something about it. So basically, we can repeat this. So the EPR, the setup for EPR is a pair of entangled particles. This entanglement will build up fire interaction in the finite time interval, and then separate them out of the causal content. And then EPR basically try to argue that the local measurement of the non-commuting observable are correlated non-locally. Okay, so you can think about this more in a more careful way, but basically it's just to say that originally we think that because these two particles are separate out of causal contact, so no matter what I've done in the particle 1 should not affect particle 2 because it's out of causal contact. But nowadays we know that because there's an entanglement between these two particles, and this entanglement is in some sense non-local. So the local measurement of non-commuting observable are actually correlated non-local. Means that the outcome of the measurement in the second system will depend on the outcome of it depends on what to measure in the system 1. So it's a very strange situation. So this is why Einstein thinks it's wrong, something wrong about quantum mechanics. Yeah. So this is why they claim that quantum mechanics is not incomplete. In what sense incomplete? Nowadays we know that later in the development, people try to argue that there is a hidden variable which we cannot observe. So quantum mechanics is not incomplete. We will go back to this quite soon. Yeah. And actually, in EPR paper, they know any word about entanglement. So the entanglement actually was coined down by Schrödinger. Okay. Also the paper in the same year, only a few months later, 3 months later, this was in August, and the EPR paper was maybe in May. So 3 months later, Schrödinger write a paper with the title here. Originally, I didn't understand the title very much. But nowadays, I have a feeling when I see this title. It says that discussion of probability relation of separate systems. We will understand what that means in the next two transparency. Okay. And in this paper, he interpreted one-side local measurement in EPR as a process. He called it disentanglement process. This in the modern days we call it the wave function collapse. So you start from the entangled state, and then after you do the measurement, the wave function collapses into a product state. Okay. So use the word disentanglement, and also he also briefly mentioned another concept which nowadays is required well studied in the quantum information, quantum optics community, called quantum theory. Means that because there is a non-locality due to entanglement, so I can change the result of the separated system by local maneuver. So in some sense, you can steer the outcome of the other partner far away from you. So this is called a quantum theory. So it's also another kind of to understand the entanglement. Okay, but in this case, it's more in the way of operation. You can define entanglement through you have operational definition for the entanglement. Yeah. So this is what Schrödinger's paper. Yeah. So you see, it's August, and it's what published in this Lawyer Society. So this paper I read it in the Lawyer Society. I think it's not only a paper; it's just a record that he reading this result in the Lawyer Society. So you see that I just highlight that he called it disentanglement. Okay, and he understand the interaction of the two representative. Representative means the wave function have become entangled. So this the word he used. And also after one page he mentioned you can still pilot the result of the separate system by local measurement. So in this word. And then he go ahead to study the relation between the probability. Okay. And we will turn into the modern language how we can understand this. So the modern days we know that the interaction actually in some sense cause decoherence, because initially these two systems maybe in the product state, but through interaction, in some sense, it's a decoherent, but actually it produces the quantum entanglement. Okay, and then you then separate them by such that they are out of causal content. So even you don't have a local interaction or non-local interaction between these two subsystems, but actually the entanglement is actually non-local, so you can manipulate the result of the other side by local measurement. Okay. So the quantum mechanics is incomplete. We also can understand this because in a sense, the subsystem in some sense cannot be described by a wave function because it's already decohered. So when we describe a subsystem, we should describe by mixed state density metric. So in the original discussion, they still think that we can describe the subsystem by a wave function even you have non-local entanglement. But this day we know that this cannot be the case. Okay. So in conclusion, we know that the quantum entanglement actually causes non-locality. Of course, this non-locality should be defined in a very causal way. It's because it's not a non-locality by interaction, it's a non-locality through entanglement.
So in the first part, the decoherence means the decoherence between what?
You have two subsystems. So because they produce the entanglement, so if you want to and then separate, in some sense, when I do the local measurement, in some sense I trace out the quantum state in the second system. So in this sense, if I want to describe the local result, actually I should use the density metric, not the wave function. Yeah, that's the key point. I realized this because I studied more on the quantum decoherence. I found it's actually the case. Yeah.
So the decoherence means tracing out.
Yeah, it means tracing out because these two systems actually are separate from each other, but they still entangled. So when I do the local stuff, I completely ignore anything out of this causal contact. So in some sense, I should trace out all the stuff. Then the right description for the local system is the mixed state density matrix, not the wave function. Yeah. So we can understand why EPR is not right, because they still try to understand this from the wave function point of view. Yeah. Of course, when you do the local measurement, it actually collapse the wave function, but actually it's a dynamical process. We can also describe that. But of course, conceptually, this may not be important, but actually, it's something like this. Okay, so this comes Bayer's inequality. So Bayer tried to understand this in a more device-independent way. Means that he tried to understand this without considering spatial setup, so that he can make a conclusion to disprove the hidden variable theory. So to do that, then Bayer introduced this kind of setup, which these days people in the quantum information science always use. We should introduce Alice and Bob, they are separate from each other. So in some sense, the Bayer experiment is a task, usually a task to correlating the input and output of Alice and Bob. So suppose at the beginning they are interact to each other and then set up entanglement and then separate from each other. And then Alice have some input X and try to get output A. And the same Bob have some input Y and try to get the output B. And in the usual sense, if there is no non-locality, we expect that the joint probability will be just a product of the individual probability. Because you don't expect the result I do here will affect the result here. So actually, this should be the inequality. Should be the equality. But in quantum mechanics, we find that it cannot be the case. It should be not equal to each other. So it means that you should modify the setup here. So you're only persistent. You insist to that this X and Y and A and B are only observable. You see, you find that in some cases you cannot satisfy this equality. You should have this inequality. So to modify, we should introduce the hidden variable theory. So in order to preserve the local reality means that I do something locally, I should not affect the system in the very distance far away from me. So I assume that there are some hidden variable which can affect to both sides through causal evolution, and which we ignore when we do the local measurement. So once I introduce this hidden variable, I can secretly say that the inequality is because actually the true relation between the joint probability and the individual probability should be right in this way. So when I do the conditional probability here, I should also take care of the hidden variable configuration. So in this sense, I can say that probably the inequality due to the ignorance of a hidden variable. Then I can explain that. So Bayer's work is trying to disprove this. Means that it should not be true even you have this kind of probability distribution. Okay. So one example is to see that actually there are many types of the Bayer inequality. The most popular one is called the CTS-NTU inequality, which after four peoples. Yeah. And this inequality is very simple. Suppose I still have A and B, and suppose X and Y can be either 0 or 1. And A and B, if I input X equal to 0, I get an outcome called A0. If I input Y equal to 0, I get outcome B0. Similar for the other stuff. And I take the average, and it's very easy to see that if this inequality is true, then it's very easy to see that this quantity should be smaller than 2. Okay. So if local reality is really the case, and really the property we should preserve for physical theory, we find that this inequality should be satisfied. Okay. However, it's very easy to find a counterexample. For example, we consider a Bayer state, which is a singular state. Okay, means that all the A and B are either 1 or -1 or 0 or 1. So we can form a bare state. And then X, Y, in some sense, it can be understood. So its particle can be a spin, qubit or spin. So you can either measure X spin or measure Y spin. Then this is very, with this setup, it's very easy to calculate this correlation function, sum of correlation function. And then you find that in this case, with this state and this interpretation, you find that the valve will obey this relation. And then in the end of the day, you see that S is 2 square root 2. So it's greater than 2, it means that it violates this bare inequality. So we know that we prepare some quantum state, it's very easy to disprove the hidden variable theory. So even I introduce hidden variable, I cannot explain this situation. And the most important is that in this case, actually this 2 square root 2 is the upper bound for this quantity in quantum mechanics. Means that in quantum mechanics, you cannot find a state which can give you a larger value than 2 square root 2. And this value are called Cherryson bound. Okay. Yeah. So this situation about bare inequality. Any questions? And actually, the entanglement actually is non-local, but we know that we still should preserve the causality, right? So even we have non-locality, which even this non-locality is not caused by interaction, but we still have some non-locality. And this non-locality should not be used to violate causality. And this condition is so-called no-signaling condition. And in the way of probability interpretation, the no-signaling condition is something like this. It means that if I only care about the measurement of A and outcome of A, and then I don't worry about what the input of B. Yeah. So this kind of condition should always true. And also similarly, if I only care about the outcome of B, I should not care about the input of X. Okay. So this condition is called a no-signaling condition. And in fact, quantum mechanics is just one of the no-signaling theories. There are many other no-signaling theories, and some theories are even non-local than the quantum mechanics. Means that some theory can violate Cherryson bound. Yeah, you can try to manipulate this probability distribution and try to work out some possible configuration. You find that the only requirement to satisfy no-signaling condition is there are some theories which are more non-local than quantum mechanics. So from this point of view, it's interesting to see why quantum mechanics is so special. Why quantum mechanics is only allowed to saturate Cherryson bound, not higher. Because all the non-locality can be used to do some quantum computation and to solve some complexity problem. So more non-locality means that we have better way to manipulate in the quantum computation. Yeah.
And so the bound is the bound for quantum mechanics?
Yeah.
Or
so
for any theory? For
quantum mechanics. Yeah, you can cook up some more non-local theory which will violate Cherryson bound. So it's not so clear why this will be the case. So a few years ago, there are people proposed that this because we want to preserve so-called information causality. This means that there is no free lunch for information when you even through quantum entanglement. So it means that if I want to send a bit of information to the other guys, I should actually use 1 qubit. Even I have entanglement share between these two partners, I cannot do more efficient work than this. Okay. So so this is called information causality. So if this is not the case, suppose if we are not using our final theory, not quantum mechanics, but something else more non-local, actually, we can get free lunch in this sense. Means that I can send only 1 qubit and I get 2 qubit information by sending only just 1 qubit through using some kind of non-local resource.